All right, we're gonna learn about volume again today, but this time it's not revolving. We're not creating washers or cylinder type shapes necessarily, but a different type of volume. It's called cross sections. So let me just warm up by showing you like what a cross section looks like. So let me try and do my best to draw some shapes here. So let me just say first, like if I had a cylinder and I was to take a cross section of this, what that would mean is like I would slice this like a loaf of bread. So yeah, 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 yeah. Okay, so I've sliced it into a bunch of pieces. Let me just pull out one of those pieces or one of these cross sections here. If I looked at one of those pieces, each little piece would be a cylinder. And so what I would be doing in these problems is just finding the volume of one of those cylinders. So one of those cylinders and then multiplying or taking an integral of that. The idea would be is you would find the area of the base, in this case a circle. So it would be like an area function, the area of the base. And then we would make it volume by multiplying the depth of dx. And then we would just take an integral of that to find the volume of all of these added together. Well, that's just one cross section. Let's say I draw a different shape. Let's say it's like some cheese or something here. And if I took a cross section and I sliced this cheese into thin slices, okay? And if I just pulled out one of those slices, then we would have a triangle here, like that, with a tiny bit of thickness, dx. And then we would have to set up the area of the base, or the area of this shape, the area of the cross section, which would be a triangle. So I could write area of the base, or I know it would be a format of something like this, like 1/2 base times height for area of a triangle, times dx to make it volume, and then we'd have some kind of way to calculate that. But now let me try and draw actually like a different kind of situation where the cheese slice maybe is clearly a triangle in the front here, and then what happens is it like goes into not disappearing, but just like smaller and smaller over here. But if I sliced this into a bunch of slices and pulled out one slice, no matter where I pulled it out, I mean, there'd be different sizes, but the idea would still be that slice right here, if I unpeeled it, it would still be a triangle here of volume to work with. So it could be a bunch of different shapes. I could continue drawing more shapes, like, let's say I had a shape here. If I slice this, pull this piece out, it's going to be some kind of rectangle of here. And then, we could set that up. Or if I have like a semicircle, and if I slice this and unfold or unpeel out a piece right here, then I have a 3D semicircle right here, which let me actually look at this one a little bit further, is I would find the area of this piece right here. So the area of that times the dx to make it volume. So the area of this is a circle, is one, or half a circle, semicircle. So 1/2 of a full circle would be pi r squared, and then make it volume by doing dx right there. Keeping in mind though, the radius is this much, not the whole length across, and then we'd have the volume of those added all up. Well, the shapes that we're gonna do here are gonna be way more complicated. Like the problems will look more complicated, but the shapes are all basic. We're gonna always be dealing with, like simple shapes like this. So that's the structure of simple shapes. We gotta keep that idea in mind of how we would set them up is actually gonna be a little bit simpler. So let me just put some stuff into our notes. So let's say our cross section is a square or a rectangle. Like, how would we know what shape it's going to be? we'll do some examples in a moment, but the way we'll know is it'll tell us, like in the problem, somewhere it'll say there's a cross section that tells you what we're working on. And then it said in this, like each is a rectangle. So it'll tell you a cross section and then it'll say the shape. There's no guesswork on what kind of shape. So every problem it'll say like the cross section is a triangle and a semicircle. So basically the formulas of the shapes are just all like square, rectangles, triangles, semicircles, pretty basic. So let's just pretend I was to do this problem if it was a square or a rectangle. So I would have an integral to find all of them. And then a square and a rectangle, we have to do like a base times height. Like right here goes, like, I mean, overall, like the idea is you would find the area of the shape times the thickness to make volume. So whatever shape they say, that area of that, or the area of a semicircle, formula goes in. So for a square, it would be like base times height would be the area of the shape, and then times dx. Now, to get that base times height, that's this length right here, that amount right there, would be like your base. And then it'll tell you if it's a square, it would be the same base as it is the height right here. Now, if you need to find that base and the height, or like find out how long this is, we'll be setting up a top minus bottom. You'll watch the videos for the examples to see. Now, let's say I was doing a semicircle. So I'd have to find the area of this shape. So a semicircle here is 1/2 of a circle. Then pi r squared, and then make that volume by multiplying by dx. So now to get that radius there, keep in mind that this length would be the radius, which you could get from maybe doing a top minus bottom, or how it is, whatever it is. And then the radius will only be half of that amount right here. Just keep that in mind. The radius is only from here to here. Now with these problems, you're not going to have any white space to work with. Like it's not like you're subtracting volume out at any point. So these formulas are just basically like this. There's no like minus some other volume, which is nice. But what's going to happen with the problems is, this is the idea of what they're saying to do, is they're going to give us an XY axis, which is 2D, and they're going to put some picture in here of a shaded region. So like, let's say this is my shaded region right here. This is basically the base of my shape, like the flat piece of the shape. And we're going to create volume by coming up out of the paper. So let's say they say, for this one, it's a cross section that is a semicircle perpendicular to the x-axis. It's not there's no like radius line. It's just the shape is just between from here to here. No matter where you draw it, the top and the minus bottom is the same. Let's say this is f of x. Let's say this is g of x. Okay, so how does this look like a semicircle? Let's say the problem was a semicircle. It doesn't at all. But what's happening is, like, we're imagining semicircles coming up out of the paper here. So this shape would come up out of the paper 3D. I don't know if I can really draw it 3D, but it would look like here. I'm trying to draw this same shape right here, like, and I'm going to try and draw it 3D as semicircles. The wider the base gets, the bigger the semicircle gets. And it would look maybe something like that, 3D. But if we pulled one of these out, it would still just be a semicircle. And that's really all we need to think about. Don't worry about what awkward shape that really creates. It's just a semicircle here. So what I'm saying is, like, this line, 3D would be the base across here, or the diameter line of this line. So this line right here would be top minus bottom. So the length of this would be f of x minus g of x would be the diameter. That's this line right here, or this line right here. So what I like to do when I'm doing these problems is I just look at this 2D shape. I draw my line from the top function to the bottom function, no white space, nothing to deal with there. And then I like to just draw the picture like this, a little bit 3D with a semicircle coming out of that line. I like to draw really dark this line and really dark this line so I know which lines match up. Now, if I was to set up this integral, I'd have to find the intersection points at A to B on my calculator. And then I would set up the formula for a semicircle is 1/2 pi and then radius squared. So the radius is half of this much. So the whole thing was f of x minus g of x the whole way across, but the radius is just half of that. So I'd have to put in here for radius squared and then dx. The radius squared would have to be f of x minus g of x would be, keep in mind, the whole thing. Divide that by 2 to make a radius, half of it. And then that would be my setup here. I could then just go ahead and plug all that information into my calculator, but I'm just gonna keep saying one more thing is, let's say I was to simplify this. I mean, 1/2 here, pi, and then if I square this, the square applies to the top and the bottom, but it looks like this on top, all in parentheses. And then if I squared the bottom, so no longer, I'm not squaring the whole bottom anymore, that's done. If I squared that, that would be a 4 on bottom. I'm just kind of doing this for fun to show how it would simplify. And then technically you could put these 2 and the 4 together and make a fully simplified setup look like this. Now, definitely do not distribute that 2 in here and here because there's a minus sign. You can't do that. All right, well, you're gonna wanna watch the videos next to see on how I do the problems in the notes, to see how I set it up. But hopefully you got the visual, like general visual, and try not to make it too complicated. Like the idea is just finding the area of like simple shapes, squares, semicircles, triangles, circles, things like that. And so if you try and visualize the 3D shape, you might get a little thrown off, but try to just avoid that complicated thinking and think of the simple setups here. And then let the calculator do the rest.